Let us derive Mayer's relation in this video. It is a very famous relation which gives an expression for subtraction between the specific heats at constant pressure and constant volume to be equal to a constant called R. R is called as ideal gas constant commonly. For that, we need to define these specific heat first. Suppose there is a sample having quantity n moles and an infinitesimally small amount of heat dq is provided to this sample. This sample is nothing but our thermodynamic system. As a result of this supply of heat, let us say that the temperature of this sample changes by an equivalent infinitesimally small amount of temperature dt. Now for this particular process, we define the specific heat as C equal to dq by dt into 1 upon n. That is amount of heat change per unit change in temperature per unit quantity of the substance. If this per unit quantity is expressed in moles, the corresponding specific heat is called as molar specific heat. Further, we can define two types of specific heats in this case. If this particular process of supply of heat dq is carried out at constant pressure, then we define the specific heat at constant pressure Cp as dq by dt at constant pressure. Similarly, if this process is carried out at constant volume, we define it as specific heat at constant volume and write it as Cv equal to dq by dt at constant volume. Of course, this factor of 1 by n is always there. If the substance is 1 mole in amount, this n simply does not appear in the formula. Otherwise, it should be there. Now, once we have defined these values Cp and Cv, let us use the first law of thermodynamics and the definition of mechanical work done and try to derive the Mayer's relation. So we will start with the first law, which says that dq is du plus dw, and we have already derived that dw is pdv. So let us just label these as equations 1, 2 and 3. Now suppose in this particular equation we keep the volume to be constant, that is V is constant. This implies dV is 0. So this term does not appear here since volume is kept constant. And if we look across this equation 2 over here, when we keep volume constant, dq can be simply written as n times Cv dt. This is just the rearrangement of the terms. So for this dq here, we should write n Cv dt is equal to du plus 0. Since dv is 0, the second term becomes 0. So what we are left with, so let us just rub it out. N Cv dt is du. Call it as equation A. Similarly, now if we keep the pressure constant and volume we allow to change. So in that case now dV is not equal to 0 because it can change. It is not constant, but the pressure is constant. So for that, from the equation number 1, we see that NCP dt is now dq because we are keeping pressure constant. So here in this equation number 3, we get NCP dt is equal to du plus pdv. Now this second term is of course not 0 because dv is allowed to change and p is just a constant, called as equation B. Now let us use equation A into equation B. Instead of du, we should write NCP dt is equal to NCV dt plus pdv. Now we need to get rid of this variable dv here because the variable appearing at the other two terms is just dt. For that, we will use the ideal gas equation of state, which says that PV is nRT. This means if we differentiate this, we get PdV equal to n and r are just constants and derivative of t is dt. So using this here gives us NCP dt is equal to NCV dt plus nr dt. Now this n just gets cancelled throughout. This Cv dt can be shifted on the left hand side. Further, this dt can also be eliminated and we are left with Cp minus Cv is equal to R. This particular relation is called as Mayer's relation and it is very fundamental to the thermodynamics related to ideal gas. Experimentally, scientists have found out the value of R for an ideal gas. It is equal to 8.31 joule per mole per Kelvin. This is just a thing to remember. So once we are through this relation, just for information, let us also know that the ratio of these two specific heats is also a constant. This has been experimentally confirmed empirically and theoretically as well in later years. This fact we are going to use in our next video. Thank you.